Welcome to this explainer. Today, we're taking those abstract lines of 8051 assembly code and turning them into hardcore, simulated hardware reality. If you've ever wondered how mere lines of text actually translate into physical blinking lights and precisely timed operations, you're in exactly the right place. We're going through a complete laboratory journey to transform you from a coder into a virtual hardware engineer.
Here's our roadmap for today. We'll kick things off with an intro to 8051 assembly, then dive into memory, registers, and flags. After that, we'll cover controlling flow with jumps and loops, set up our Keil and Proteus integration, and finally, master those tricky timers and counters. Let's get into it.
Section 1. Intro to 8051 Assembly. With all the high-level languages out there today, you might be wondering, why on earth are we writing assemblies specifically for the 8051? Well, it's all about absolute low-level control. You get a level of specific architecture optimization and precise timing that higher-level languages just can't touch. Plus, and we all know this, when things inevitably crash, knowing assembly makes your debugging so much sharper because you actually understand what the hardware is doing behind the scenes.
Moving on to Section 2. Memory, registers, and flags. So where does all this data actually live? Well, before we map out the whole memory, we really need to talk about the PSW, or Program Status Word. Think of this 8-bit register as the microcontroller's vital signs during math operations. Now, the 8051 only actually uses 6 of these bits, but man, they are absolutely crucial. You've got the carry flag for when an operation spills over that 8th bit, the auxiliary carry, the parity flag tracking the number of ones in the accumulator, and the overflow flag for sign numbers. It's basically the brain's real-time reaction to whatever math you throw at it.
Now, when visualizing the 8051's 128 bytes of RAM, I like to think of it as a highly organized microcity. Down at the very bottom, from hex location 00 to 1F, we've got 32 bytes dedicated to register banks. These are our heavy lifters, our workers, with bank 0 being the default on power-up. Right above them sits 16 bytes of bit addressable memory. And finally, from 30 hex up to 70 hex, we have 80 bytes of scratchpad RAM. That's essentially the worker's workbench for storing all your everyday data and parameters.
Here's where it gets really interesting. When we use push and pop instructions, we're actually stashing our worker's data temporarily on the stack. And where exactly is this stack? Well, by default, the 8051 squeezes the stack right into register bank 1, sitting directly on top of our default bank 0. It is just such a beautifully efficient use of some very tight real estate.
All right, Section 3, Controlling Flow, Jumps and Loops.
Okay, microcity established, data organized, now we need some action. Here's a classic problem. We definitely don't want to manually copy and paste 1,000 lines of code just to create a simple time delay for a blinking LED, right? So we need a smart way to tell the hardware to just repeat itself efficiently.
The magic bullet here is looping. But there's a catch. Because the 8051 is strictly an 8-bit system, a single loop register maxes out at 256 counts, that's it. So, if we want to create a delay you can actually see with the human eye, like waiting a full second, we have to nest those loops. By dropping a loop inside another loop, we multiply those 256 counts to build up some seriously substantial time delays.
And check out how conditional jump instructions let the 8051 make smart, on-the-fly decisions based directly on those PSW flags we talked about earlier. Take DJNZ, decrement, and jump if not 0. That right there is the absolute powerhouse instruction for running our loops. The code literally reads its own status flags to figure out, hey, do I loop back around or do I move forward?
As things get more complex, efficiency is the name of the game. The LCALL instruction is fantastic for this. It lets our main program jump entirely to a separate delay subroutine somewhere else in that 64K memory space. Then, once the delay finishes, the RET, or return instruction, kicks in, and boom, control goes seamlessly right back to where we left off in the main code. It's proper, modular programming right at the bare metal hardware level.
Moving on to Section 4, Keil and Proteus integration.
Now for the fun part, crossing over into actual visual hardware simulation. This workflow bridge is simple, but it's a total game changer. We write our assembly or C code in the Keil IDE. Then we compile that down into a hex file. Link that file to our microcontroller in Proteus and hit play. We're not just writing text anymore, we are bringing a circuit to life.
Quick pro tip though, and do not skip this. You absolutely must ensure Create Hex File
is checked in your Keil output options. Why? Because Proteus does not understand assembly or C. Those raw hexadecimals in the hex 80 format are the literal, physical instructions that Proteus needs to simulate the actual silicon. But even before we jump into Proteus, Keil gives us some ridiculously cool tools. Through Keil's debug window, we can pop open the peripherals menu for port 2 and literally watch the bits toggle high and low in real time. It's an incredible way to verify that your logic is manipulating the pins exactly as you intended. And here is the payoff. When building out a Proteus schematic, we can drop our 8T89C52 microcontroller right in the middle, hook up a crystal oscillator, some capacitors, a reset button, and an LED array on port 2. By linking our Keil HX file directly to that chip, our abstract logic physically manifests as blinking LEDs right on the screen. I gotta say, it is endlessly satisfying to watch your code physically light up.
Finally, Section 5, Mastering Timers and Counters.
Okay, so if we want our LEDs, or really any operation, to fire off at perfectly exact intervals, we have to master hardware timers. And yes, that means a little bit of math. In the classic 8051 architecture, one machine cycle takes exactly 12 oscillator periods. So if we take our standard 11.0592 MHz crystal and divide it by 12, we get 921.6 kHz. Flip that, and you get a beautifully precise 1.085 microsecond machine cycle. Nailing the specific math is what lets us design delays that sync up flawlessly with human perception.
So how does that math look in the code? Well, first, we configure the timer mode register, or TMOD, setting it up for our required operation. Then, relying heavily on that machine cycle math we just did, we load very specific hex values directly into the timer high and timer low registers, TH0 and TL0. We're essentially preloading the timer so it overflows and trips the timer flag at the exact millisecond we want it to.
And just to prove we got it right, Proteus offers the ultimate sanity check, a virtual digital oscilloscope. Hook this up to the circuit, and you get absolute visual proof. You'll see perfectly crisp, evenly spaced square waves right on the display. That is not some sloppy estimate from a nested loop. That is a precise, hardware-driven signal born directly from your assembly code.
We really covered some serious ground in this explainer today, from mapping out RAM and registers to wrangling loops, right up to simulating full hardware setups with Keil and Proteus. You've basically mastered the journey from raw memory architecture to simulated physical reality. The foundational skills are all there. So the question is, what are you going to build next?